project named Constellation Connection, and the problem of our project is that we are given a network of stars and we're trying to find the shortest light distance path between two stars if light can only travel through the existing neighboring stars' connections. And my name is Diya. So when we run our project, you'll see a default of 400 stars appear on the display, and then the user can go ahead and pick either algorithm, and you will see when they hover their mouse over the algorithm, it does like a little highlighter. And so let's say they pick the first one, they can enter stars. I'm gonna enter 222, and then they have to press return or enter on their keyboard, and then the stars will automatically update to whatever number the user set. Then they can go ahead and press generate, and you can see that a line will form. This line is formed using our back-end logic for both algorithms, and you can see that the info box will also update. And then the user can choose to pick the second algorithm and press generate again, and the info box will again re-update with the newest information. And I'm gonna go ahead and show you examples with other stars. So if the user decides to enter a number of stars less than 20, let's say 5, and they press return or enter, it will automatically bump them up to 20 because I set the minimum star limit to 20 just for better results, and they press generate, and the algorithm should work the same way. And for the last example, I will show if they enter more than 500 stars, that'll bump them back down to 500. So they pick an algorithm, enter 505 stars, press enter or return, and they click generate, and it will still show them the line and everything just like before.
Hi, this is Charley to talk a bit more about specifically the two different algorithms that we're comparing, which are Dijkstra's algorithm and the A-star algorithm. They both complete the same task, which again is to find the shortest light path distance between two stars if light can only travel through existing neighboring star connections. So since they both complete the same task, that means that their visualized shortest path remains the same. So if you can see, if I generate it for 500 stars for Dijkstra's here, it's an orange path, but then for A-star, I'll generate it again, it switches to a red path because we used color to symbolize like that we're using a different algorithm, but you can see it's still the same path because again, they're achieving the same goal. However, the key difference is you can see that over here, we listed the number of nodes explored to find the shortest path because that's like the key difference in the algorithms. It's that A-star uses a heuristic to try to predict the shortest path and explore less nodes in order to find it. So they're easily compared right here. You can see A-star only explored 288 like star nodes, while Dijkstra had explored 308 to find it. And yeah, so basically they both have the same worst time complexity, like worst case time complexity, because in theory, A-star might end up having to explore the same amount, but because the heuristic, which, is based on like the star's distance, helps predict this, it generally has a better average time complexity and better performance by exploring less nodes.
Hello, this is Samantha. I will be talking a little bit about how we went from the data to the visualization. Something important to note is that the information panel has the X and Y coordinates displayed, but the algorithms take into account the X, Y, and Z coordinates. While the 2D visualization may not appear to be the shortest path here, it is the shortest actual path calculated using all three of those position coordinates, and we found that distance using information from the data set being the sky longitude, latitude, and the apparent shift in position.